photosynthesis because the way we get the hydrogen that goes into this CO molecule right here, right? So we have a CO2 molecule, and here we have a CH12O, C6H12O6 molecule. We need some hydrogens to add to these carbon molecules, right? Those CO2 molecules. We get them from water. But what we don't need is just as many oxygen molecules, because we already have more than enough oxygen already, right? What's the ratio of carbon to oxygen and glucose? 1 to 1. CO2, 1 to 2. So we already have more than enough oxygen. What we need is hydrogen. And remember, the act of reducing is reducing the amount of bonds between carbon and oxygen, right? So we're going to get rid of some of those oxygen molecules. The point is, we get that hydrogen by breaking up water. The oxygen that is released, or at least a significant majority of it that is released from the process of photosynthesis, is done so by hydrolyzing water, by breaking up water. And that's the first thing we have to do in photosynthesis. But like I said, that entire process would involve at least a day, if not 2 days, of discussion in a regular biology class if you really wanted to go at any level of depth to understand how photosynthesis actually works. If you want to hear an interesting thing that I saw on YouTube, and I can point you in the direction of it actually, about how Earth might have been purple at one point, which is particularly poignant for me because I like purple. And is also interesting to explain why photosynthesis, as energetically efficient as it is actually much less energetically efficient than it could be. And it's an interesting hypothesis that I could talk about, but after we're done talking about this.
All algae-based?
Yes, actually Archaean-based, but yeah. We talk about it after class, but it's kind of neat. And I can point you in the direction of the YouTube video, Purple Earth. You could probably find it just do a search for Purple Earth. Like I said, it's a hypothesis, because it's hard to find evidence of fossilized Archaean bacteria. Respiration is simply the act of moving in the opposite direction. When you guys think of respiration, what do you think of? Do you think of the cellular act of combining oxygen with high energy carbohydrates in order to release captured energy in the form of ATP? Or do you think of
Context.
Respiration, the reason why we breathe, the reason why we have lungs, is to provide oxygen to our cells so that they can undergo this process right here, to break down sugars into energy. Not in the form of sunlight, but in the form of ATP, which you can then use to pay for everything else that you need to do. We breathe to provide oxygen to cells so that they can respire. Because your lungs don't care about oxygen. It's the rest of your body that needs it. Your lungs are there to provide it. How about some different types of carbohydrates? This is where that concept of that macromolecule comes in, because a saccharide is the individual functional unit of carbohydrates, a single simple sugar. And so a single simple carbohydrate would therefore be called a monosaccharide, because there is only one. Monosaccharides have one sugar in them. A disaccharide, therefore, would be that a similar monosaccharide but repeated twice. So a disaccharide has 2 sugars in them. And then we jump all the way to polysaccharides, because they have 3 or 4 or 5 or 6,000. Because it just goes up from there. And these polysaccharides can get very, very large. But they are all built by combining monosaccharides together over and over and over and over and over in a chain. Monosaccharides are carbohydrate molecules with 3 to 7 carbons. Here's an example, erythrose, which is an aldo carbon, an aldose carbon, aldose sugar. How do we know it's an aldehyde or an aldose sugar? Because, well, where is that double bonded oxygen? Is it in the middle, or is it in the end? In this case, it's at the end, and that's what makes it an aldehyde, right? As opposed to a ketose, or a ketone sugar, which says that same double bonded oxygen, right? But where is it bonded? The carbon that it's bonded to is not at the end, it's...
Chapter 26.
In the middle. Audio book.
It's Harry Potter.
Good reads. So, we have aldose sugars, or aldose, which are sugars that when drawn in this manner have that double bond at the end on a terminal carbon in the form of an aldehyde. We have ketose or ketone sugars where that double bonded oxygen is instead on one of the middle sugars, or more specifically not on a terminal sugar, right? Now, what do you notice about every single carbon that, other than the one that has the double bonded oxygen to it, what do you notice about every single one of those other carbons? They all have hydroxyl groups. Every single one of those other carbons has a water bound to it. Do you see the water on either side of that carbon? HOH. A carbohydrate is going to have that ratio because that's the way it works. If you're not that double bonded carbon right there in a linear form, then you are going to have a hydrogen and a hydroxyl bound to every other carbon. That is one of the defining aspects of monosaccharides. And the reason why that's important is because later on we will talk about the reduction or oxidation of sugars to make things that are no longer monosaccharides. They are now acids or carboxylic acids or otherwise, so they are something other than a simple monosaccharide because they have been either oxidized or reduced. We classify monosaccharides by the number of carbons that are present, so triose, pentose, tetrose, hexose. This is very similar to how we would describe an alkyl group, right? Except instead of hexane, it's hexose. So triose, 3, tetrose, 4. It's a little bit different because it wouldn't be tetrose if there was an alkane. What would it be? Bute, right? Exactly. Here we have glyceraldehyde, aldotriose, threose as a specific name, also an aldotriose, ribose, aldopentose, fructose, ketohexose. Anybody know what a deoxyribose sugar would look like? Why am I bringing this up in terms of ribose? Ribose is a sugar that forms the backbone of one of those other large macromolecules that I mentioned, DNA, nucleic acids, right? Just nucleic acids as a group, DNA is a specific type of nucleic acid. Ribose is the sugar that is found in that monomer, which is in the form of ATP, UTP, TTP, which is adenine triphosphate. It's that ribose sugar that's in the backbone of that. It's the three phosphates connected to a sugar, connected to adenine or uracil or thymine or whatever other base it is that we're talking about. Deoxyribose is almost exactly the same as this, but the two little words in front of ribose there, two little letters, D for deoxy, implies that there's what? Less oxygen. One of these, not that one there, but one of these oxygen molecules has been removed, and so we have a carbon with two hydrogens. Deoxy, we have removed an oxygen. We're not going to get into why that's important here. We talked about DNA in the last section of this class, and we'll talk about the significance there, but I wanted to point it out since we have ribose right here. It is a 5-carbon sugar. Fructose, hexose, we have 1, 2, 3, 4, 5, 6 carbons in this guy. But what's different about fructose? Where is the double bonded oxygen? Is it at the end? Nope. It's one of the ones in the middle. So this is a ketose as opposed to an aldose. This is a sugar that has the double bonded oxygen on a carbon that does not have a hydrogen. It is not terminal. This will be important in a little bit. All right, so that's an introduction to carbohydrates as a group, what makes them up, i.e. monosaccharides, and a basic understanding of how we classify some of the larger molecules as we put some of those things together with a few examples. In order to understand why sugars are different, we have to understand the idea of chirality. is something that has been brought up previously, but we have not yet discussed. You might remember it somewhat from previous chemistry discussions. Chirality has something to do with left-hand and right-handed. In other words, what we have are things that are mirror images instead of superimposable things. Now, we've talked about how things can just be flipped and turned around before. For example, why is it that we can have a 2-methylbutane, but never a 3-methylbutane? Do you remember this? Butane as a molecule has how many carbons in it? 4. Right? So here's our 4 carbons. 1, 2, 3, 4. Now, this would be a 2-methylbutane, right? We have a methyl group coming off that second carbon. Why is it that we would not ever have a 3-methylbutane? Right, because it'd still be 2. If I took this guy and just flipped it around, I could spin this and it would look exactly like that, right? And so it is not a mirror image, it is something that can be simply turned on an individual axis to create exactly the same molecule, which means it is exactly the same molecule. But chirality introduces the concept of molecules where you cannot do that, where you cannot take a molecule and simply spin it to get something that is exactly the same as what you started with. A mirror image is one way of looking at that. Your hands are mirror images of each other. They line up like this as if there was a mirror in between them, but you cannot place both of your hands out facing the same direction and then put them over each other and get the same thing. They are not the same. And even if I were to spin this so that it looks like they might be the same, if I superimpose them, they are still not the same because here my palm is facing up and here my palm is facing down. They are not superimposable. They are mirror images of each other. Now, how does this apply to chemistry, you ask? Good question. Let's talk about it. So, here we have ethanol. Here we have dimethyl ether. These are not mirror images of each other, but they are something we have previously discussed called structural isomers. In other words, both of these guys have the same chemical formula, C2H6O, right? But we can have that as an ethanol molecule, or we can have that as dimethyl ether. Both of these are C2H6O. These are not mirror images. They are also not superimposable. They are structural isomers. In other words, if we take these Legos, we can build more than one molecule from them, right? But those are structural isomers. They are built differently. The same is true down here of propanol and propanone. Here we have a propanol, and propanone. Here we have an aldehyde. Here we have a ketone. But their molecular structure, as far as their chemical formula, is exactly the same. The way we get into these mirror image things is where we have the concept of a structural isomer, but it's not the same thing. Now what we have instead are things that still have the same exactly molecular formula, just like structural isomers do. But now they're bonded the same way, but they have a different arrangement in space. These guys have a different arrangement of atoms. Structural isomers have this as the same, but these things are completely different. Stereoisomers have the same three-dimensional orientation as far as what order they come in, but the way in which they are arranged in space is what might be different, which could imply that the three-dimensional orientation is different, so I probably shouldn't have said it that way, so forgive me. These guys are where we get our mirror images of that. When we get mirror images, instead of superimposable, that is where you get chiral molecules. So chirality is an aspect of non-superimposable stereoisomers. That might make more sense if we look at things in terms of hands again, or actual chiral carbons, as we will in a moment. Same number of atoms arranged differently to create a non-superimposable mirror image. Your hand has a central palm, 4 fingers, and a thumb. But the way in which we arrange that to create a mirror image means that the end result is not superimposable. That is where that aspect of chirality comes in. So therefore, hands are a good metaphor of chirality because they are mirror images of each other and not superimposable. Now you can get things, you can get molecules where the mirror images are identical and are superimposable. And that is then called, therefore, achiral or not chiral. So you can use a mirror to project anything. Hold anything up in front of a mirror and you'll get the mirror image of it. The difference is if you can twist that mirror image back again to superimpose it, if it can just overlap it, then it's still the same thing. If you can't do that with a mirror image, then you have something that is chiral. So an example here, your gloves, chiral, your shoes are chiral, but those two glasses are not. They're achiral. We can put a mirror image to project them, but then that mirror image is still superimposable over the original. Therefore, it is not chiral. All of these, of course, are metaphors, not literal chiral molecules. So, what does it take to be chiral? A molecule is considered chiral when it has at least one or more carbon atom that is chiral. Now, in order to be that carbon atom in question has to be bonded to 4 different groups, and also non-superimposable mirror image. It still might not make a lot of sense to you. So let's look at a molecule here. Here we have a carbon bound to a hydrogen, a bromide, a bromine, chlorine, and an iodine. When we take a mirror reflection of that, the thing, if you think about it, if you're looking at this in terms of you are this central carbon, you've got a chlorine in your left hand, you've got an iodide in your right hand, and that bromine's pointing out the back, like a tail, and the hydrogen is on top of your head, right? Now when we mirror image that, in the mirror image, the chlorine is now in the right hand, right? The iodine is now on the left, the bromine's still in the back, and the hydrogen's now still on the top, right? But if we take that mirror image and we flip it, they are not superimposable. Because on this side, my right hand was holding what? The iodine. But on this side, my right hand was holding what? The chlorine. And so if I take version A of myself and version B of myself, and we both turn to look at you, and then I slid over in front of my mirrored twin, my right hand would not be holding the same thing. Correct? So therefore, we would not be superimposable even though we are mirror images, which is what this right here is supposed to show you. So, when that happens, we create 2 different molecules that we call enantiomers. So there are 2 enantiomers of this particular molecule. An enantiomer is a version of a chiral molecule. There can be more than 2 enantiomers for a chiral molecule. Every different way that you can change the order in which things are bound together around chiral carbons creates a new enantiomer. This is simply an example of 2 for this exceptionally simple carbon. Here's the thing though. This carbon, if you replace that iodine with a bromine, now both my left hand and my right hand are holding a bromine. The back is a chlorine, the top is a hydrogen. When we mirror project this, my left and right hand are both holding bromines, and I have a chlorine in the back, right? But if I just take that guy and rotate it just a little bit, just spin it around, then suddenly what I would get is exactly the same molecule that I had in the back, on this one, on the one that I started with over here. So this is not chiral.
Where's the iodine?
It's gone. This was the one with the iodine.
Okay.
Here we have replaced it with a bromine. So now we have 2 that are exactly the same, and because of that, we can take this guy right here that is a mirror image, right? But all we have to do is just grab that hydrogen at the top and just twist them around a bit. And now we have something that looks exactly the same as what we started with before we had the mirror image, right? Superimposable. Could we do this back here? What if we took this hydrogen and just went and turned it the same way? If I turned this to the right so that that chlorine moved over so that it was over here on this side where the bromine is now, that would mean is both of these two things would shift to these two positions, right? So the iodine would be in the back and the bromine would be in the front. Is that what we had over here? No. Here the iodine's in the front and the bromine's in the back. So that twisting thing, just that spinning mechanism, does not create a superimposable molecule. But here it does. All we have to do is twist it. And now what we have is what we started with. That means it is not chiral. So, let's take all that, our understanding of chirality and the generation of enantiomers, and let's apply it to an understanding of sugars. But before we do that, let's talk about a way that we draw these sugars as we move forward so that we can all be on the same page for understanding what it is that we're looking at when we look at these sugars. So to do that, we're going to use Fisher projections. This is somewhat specific. It's going to look a lot like what we've seen before, but it's a specific way of drawing sugars. A two-dimensional representation of a three-dimensional molecule. The important thing here is that we're going to place the most highly oxidized carbon. Tell me what that means. What's the most highly oxidized carbon in a sugar molecule? What's the most highly oxidized carbon in any hydrocarbon? Carbon with the most what? With the most bonds to oxygen, right? So, we are going to take the most highly oxidized carbon group and we're going to put that at the top, if at all possible, or as close to the top as possible. We're then going to use vertical lines to show bonds that are going back and horizontal lines in place of wedges for bonds that come forward. What's that look like? Kind of like this. So here we have something, we've seen something kind of like this before, but instead of a dashed line, we had that kind of dashed triangle, remember? We had the one where we had two things on the plane and then one that was going back and one that was coming at us, right? Well, here we've done the same thing with this central carbon, but what we have done here is we have shown that we have bonds that are going backwards away from us and two bonds that are coming forward. So this is a way of attempting to show a three-dimensional orientation, but still drawing it on a single plane, so that we can see which ones are going back and which ones are coming forward. If we project that through this mirror, we're going to get those same orientations of which ones are coming away towards us, which ones are going away from us. In both of these cases, what we have created is a chiral carbon. Because here we have now defined a molecule that is showing us the orientation of the carbon bonds. And by doing so, you can see that this molecule right here, if we took this thing right here and just twisted it, turned it around, we would not get exactly that. Why not? Because here, this hydrogen and this hydroxyl are pointing at us, right? And the top carbon and the back carbon, they're pointing away from us. If we took this thing from the top and just spun it, those two carbons would now be pointed towards us. And these two side groups would now be pointed away. So if you took that thing after we spun it and put it on top of this, would it be exactly the same thing? No, it would not. So that makes them chiral. That means that that carbon right there is chiral, which makes this three-carbon molecule chiral. And so here we have what we have labeled L-glyceraldehyde and here D-glyceraldehyde. Another way of thinking about D is instead of calling it D, we might call it R. For left-handed or right-handed. And we're going to get a slide that tells us all about how that actually works, but can you already tell what is left-handed and what is right-handed about this molecule, this very simple 3-carbon sugar? What's on the left here? And what's on the right? The hydrogen, or in this case, actually what's more important is in fact the hydroxyl. Here the hydroxyl is on the left, and here the hydroxyl is on the right. That is L, glyceraldehyde. This is D, glyceraldehyde. So, D or L isomers are assigned on the position of the hydroxyl group the furthest away from the carbonyl carbon. Tell me what I just said. Which carbon is the carbonyl carbon?
Furthest away.
We count the hydroxyl on the one furthest away from the carbonyl carbon. Okay, that's great. Where's the carbonyl carbon on those two examples that we have at the bottom of this slide? What's a carbonyl? Because we didn't really take the time to name that functional group when we were talking about aldehydes and ketones. The double bonded carbon, the double bond C-double-O. The C double bonded O carbon, that's the carbonyl carbon. So, when we talk about that, remember when we described how to draw these things, we said put the most oxidized carbon at the top. How many oxygens is that carbon bonded to? Just one, right there. 2 hydrogens, an oxygen, and another carbon, right? How many oxygens is that one bonded to? Just one, that hydroxyl. That one there bonded to just one, that hydroxyl. How many oxygens is that one bonded to? 2, because it has a double bond. That's why it goes at the top. Now that works for an aldose sugar, right? Because that puts a double bond all the way at the top. It doesn't work quite so well for a ketose sugar because that would be bonded to one down here, so it's going to be, but we're still going to put that carbon as high as we can in our projection. But the L and the D is determined by the hydroxyl furthest away from that chain. Right there. Not counting, okay, let's be a little bit more specific. The chiral carbon furthest away. Because here's the thing, this guy right here, he has a hydroxyl, right? It's right there. Why is that carbon not chiral? Why does that carbon not count? Well, it doesn't count because it's not chiral. I just answered my own question. Why isn't it chiral? Thank you. Why isn't it chiral though? It doesn't count because it's not chiral. Why isn't it chiral?
Because it can only appear that one in that one configuration.
Because it can be twisted around. That carbon can be twisted around to match this one. More specifically, something that hasn't been mentioned quite yet, but we'll get to it. Actually, I think we're a few slides away from it. We'll get there. Point is, we had a hint back with that 2-bromine. Remember that one single carbon that had 2 bromines? In order to be chiral, that every carbon has to have 4 different groups attached to it. So when we had a hydrogen, a chlorine, a bromine, and an iodide, when we had 4 different things, that could be chiral. But if we replaced one of those and instead had 2 bromines, all of a sudden that carbon wasn't chiral anymore. Because now the mirror image could be projected. That carbon is not chiral because it has 2 hydrogens. What are the other 2 things attached to it? If I'm going to draw that carbon all the way at the bottom with 4 bonds, what are they going to be? 2 of them are going to be hydrogens, right? Because we've got CH2. All right, so what's left? Well, we still have an OH, right? So that's going to be our 4th bond. Or a 3rd bond, I should say. What's the 4th bond?
Carbon.
Carbon, and not just carbon, but actually all of that. is the fourth thing. In the same way that I didn't just put an O here, I put an OH. All the rest of that molecule is the other thing hanging off the side. But point is, this carbon right here, if I mirror imaged it, I could just spin it back around again and get the same thing, couldn't I? Just like the two with the bromines. So it is not chiral. To be chiral, we have to have 4 different substituents. So that is why that carbon doesn't count as chiral. It doesn't count on our furthest away because it can be either orientation that it wants. It can spin around. It can rotate and have either orientation that it wants. So here, the last chiral carbon, that hydroxyl is on the left, that makes it an L. Here, the last chiral carbon, the hydroxyl is on the right, so it makes it a D. But wait a second, see? Let's look at this carbon right here. What are the 4 things that are hanging off of that carbon? We have 1 hydrogen, 1 hydroxyl, right? But it's got a carbon here and a carbon there, so why is it chiral? Because remember, it's not just the carbon. It's got this here and that there. Does that equal that? This is CH3O2. This is CH3O. It's not the same thing. And even if it did have the same structural, even if it did have the same chemical formula, if the structural isomer was different, it would still be different. What matters is that these 2 ends are not superimposable, are they? And so therefore they are different attachments, they are different adjuncts, they are different molecules, if you will. And so therefore it makes that carbon still chiral. It has 4 different things bonded to it.
Why L and D?
L is left, and D is R. Left-handed, right-handed. I don't know specifically why D instead of R.
I think at first it might be Dexter, but Dexter's left, so.
I don't know. I'm sure there is a reason, and it probably has an interesting colloquial, if not funny, anecdotal chemistry meaning to it. I don't know. All right, so why is this important? Enantiomers are very common in biological systems. Find it already?
Dexter's left for right.
Ah.
Sinister is left.
There we go. As I say, it's probably a very easy thing to find. I just didn't know.
Yeah, if you've done some heraldry.
Or had Google. So, enantiomers, okay, forgive me. What's an enantiomer again?
Same number of atoms. It cannot be superimposed.
Right, it cannot be superimposed. So an enantiomer is a word that we use to describe a non-superimposable mirror image of another chiral molecule. That's a really long description. An enantiomer is simply the word we use to describe a chiral molecule. You can't be an enantiomer if you're not chiral. Follow? If you are chiral, then you can have a handful of enantiomers. The more chiral carbons you have, the more enantiomers you can possibly get for that molecule. So, when we're talking about respect to biological systems, we're really only worried about that last chiral carbon and whether or not the hydroxyl is pointing left or right in that Fisher projection. If it's left, it's L. If it's right, it's D. This will become important in a little bit. Are there more enantiomers than that, technically? Yes, but those are the ones that are important for biological methodologies for biochemistry. Here's why. when you're talking about biochemistry, a lot of these biological molecules are chiral, which means that when they come together to form the specific shapes of enzymes that do 99% of the work in your cells, enzymes that do 99% of the work that is necessary to be alive, those molecules are made by chiral molecules, which means that the active site, the shape of the functional part of that enzyme, is also going to be chiral. Now this is overly simplified by implying that this enzyme has an active site with a circle-shaped keyhole, a square-shaped keyhole, and a diamond-shaped keyhole or triangle-shaped keyhole. So in this case, this particular molecule, in order to fit into that keyhole, has to have a circle shape, a square shape, or cube, I should say, and a sort of pyramid-shaped thing in the right orientation. This chirality will do it. Is this the same molecule right here as this? Structurally, they are the same, right? It's got this same weird guy up here, this pentose ring up here, we have a carbon in the center, and we have 3 different guys down here. We have 4 different things attached to that carbon. But they are not superimposable, are they? They are enantiomers. This guy right here will not fit into this active site because a square box will not fit into a spherical hole. Unless it's a really small square box, but that breaks the metaphor. So, this enantiomer will fit in that active site. That enantiomer will not. And so if your biochemistry requires something to fit right there in order for it to be functional, in order for that enzyme to be able to do its job, then it won't be able to do anything to this guy. Because it doesn't fit there. Here's the thing. When you burn when you burn wood in a fire, all the chemical reactions that are occurring right there are also occurring inside your cells. All the energy that is being released from all of that carbon in that wood is being released as heat. That's what the fire part of fire looks like. We see it as heat, as light given off by not so black body radiation. Which, if you don't know what that means, forget it, never mind. But still, the point is that those same reactions are occurring in your cells, but they are occurring one by one in the presence of an enzyme so that the energy, instead of being lost as light and heat, can be captured as energy and eventually converted into ATP so that you can use it to do the things you have to do to survive. But if those molecules, if those sugars don't fit in those enzymes, then we can't do anything with them. Which means we can't break them down, which means we don't get any energy from them, which means we would die. Enantiomers in biological systems are very common. And therefore, different enantiomers for the same molecule can have very different biological effects. For example, this is a chiral carbon. This is the same chiral carbon. This is L-dopa, this is D-dopa. This is used to treat Parkinson's disease. L-dopa. L-dopa is a precursor that when it gets into the brain is converted into dopamine, so it can raise serotonin levels. So one of the problems with Parkinson's disease is they have critically low serotonin levels because they have a breakdown of the type of cells that produce dopamine. It's hard to treat diseases of the brain because your brain is highly protected. There's this thing called the blood-brain barrier, which when I was a kid I used to think it was like this plastic sack that surrounds the brain. Totally not like that. The blood-brain barrier is effectively just all of the capillaries that are feeding your brain, the epithelium, or I should say the endothelium of those cells are very tightly sealed. They are very close. It's like the bouncers at a really strict club. You can't sneak in. You've got to go through the bouncer. The rest of your body is like a club that has a bouncer out there, but it's mainly just to look important, and he doesn't really care, and it's really easy to sneak past him. Multiple doors maybe, slip in the 20, whatever, you can get in no problem. I obviously have a lot of experience with this metaphor. Not really. Like, I watch some TV. But that's the way it works. The rest of your body, most of the rest of your body, your capillaries are fairly leaky. They'll let things in and out. In fact, that's half of their job. But in your brain, they do not. Because your neurons in your brain are very, very important. And so they will only let very select things through to get access to your neurons. That's why it's easy to get a drug that can help us down here. It's hard to get a drug that can help us up here. Because you have to make something that will have an effect when it gets there, but can actually get there. L-DOPA, when it gets there, is converted into dopamine. D-DOPA is not. And the only difference here is, well, we've got an H and an N2 right here. They're projected in different directions. We have our carboxyl, so we have a different projection for which way these things are pointing around that central carbon. But structurally, these things are the same. If I drew this without an appreciation for forward or reverse, you could invert this and they would be exactly the same molecule. But because of our understanding of the fact that these things are not on a single plane, that all of these things have projections, this is going back, that's going forward. If we twisted that around, if we took this and just twisted it, spun it, the NH2 is in the back, but where would it be if we spun it? It'd be in the front. What's in the front over here? The hydrogen. They're not superimposable. And that tiny, simple difference means the difference between a chemical that can be used to treat Parkinson's and a chemical that has no effect. For a long time, when we made these drugs, the chemistry that made them made both enantiomers. The biochemistry that synthesizes this molecule also synthesizes this molecule, especially if we do it en masse. If we do this synthetically in jars, it's going to make both of these. But only one of them actually works. So nowadays, what we do is we use chiral filters so that when we make these active enantiomers, we purify them down so that we're either only making the right chiral version, or we remove all of the wrong chiral version so that the drug you're getting is only the active form of that drug. There's a lot of different techniques that can be used to do it, HPLC and otherwise. It's some really interesting stuff, goes way deeper than what we have time for. What would be the easiest way to do this to ensure chirality? Well, the reason why we care is because biological systems care about the chiral nature of their molecules, right? So what would be the easiest way of making sure that we get a biologically pertinent chiral shape? Well, what if we used chiral enzymes to make it? They would make just that one chiral version, right? And that's what they mean by chiral technology. We can either make it both ways and purify it, or there are some places that are sort of engineering enzymes, putting these enzymes together so that they can make these products. And if it's made by a biological enzyme, it will only make one version. Because the enzymes are chiral. They will only attack to make that reaction from one specific side, meaning they will always make the same chiral version. As opposed to if you just have random attack, it could attack from either direction, and therefore it could make either version.
Could you also introduce it to something that has receptor sites for the one isomer and no receptor sites for the other, so that all that's left in the solution is the other?
If you could engineer a receptor that binds to the one you don't want, yeah, you could do something like that. And that's actually kind of close to the way the HPLC filters are. They just use certain chiral centers because chirality has an affinity for each other. And so if you fill a tube with D chiral substituents versus L chiral substituents, what you get, where did I go? Here we go. So L-dopa is the one that we want. So you fill it full of D orientation chiral molecules, and the D-dopa will move through the filter slower than the L-dopa. L-dopa goes through really fast, and D-dopa takes a much longer time. So you can purify that way as well. Or you can just make it using enzymes that only synthesize it in a certain orientation, but that's really complex because your brain doesn't make L-dopa, it makes dopamine. But the difference is this is converted into dopamine in your brain by similar enzymes, but those enzymes don't know what to do with this because it's not the right shape, because it doesn't have the right orientation of peg and hole.
You're describing my narcolepsy drug.
Yes, very much so, yeah. Which is why I was like, we'll get there. We just didn't get there that day. So, for a lot of drugs, only one enantiomer is biologically active. So let's take all of this and start applying it back to sugars. This is glucose, galactose, and fructose. How many sugars does each one have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
You said how many sugars?
How many carbons, excuse me, does each sugar have? Yeah, that would, I can see why that might have been a confusing question for you. How many sugars does a sugar have? 1. These are all monosaccharides, by the way, so that would have technically been the correct answer to the question I asked you. 1. Each of these sugars has 6 carbons. They've numbered them all for you. Now, we have put the most oxidized carbon up here at the top, but we couldn't do that with this one because, well, the most oxidized carbon's right here, right? But it's not the first one in line, but we still put it as high as we could, right? So that's what they mean by put the highest oxidized carbon at the top. It's still got to be in a line like this, so the most highest oxidized carbon is as close to the top as it can get here. Because we can't take this guy, pop it off, and put it down there. Doesn't work that way. At least not yet. Now, this is D-glucose, D-galactose, D-fructose, as opposed to, what's the other letter other than D?
No.
L, which, for our purposes, is left. So how do you know that this is D-glucose? Well, here's your carbonyl group. So where is the chiral carbon furthest away? That's number 5. Which direction is the hydroxyl pointing? To the right, which makes it D. So it's not L, right? Here, same thing. Here's our carbonyl. Here, down here, our furthest away chiral carbon. What direction is the hydroxyl pointing? Right. Same thing for fructose. Here's our carbonyl. Furthest away, what direction's it pointing? Right. So it's D-glucose, D-galactose, D-fructose. Aside from that, what's the significant difference between the rest of these? Especially glucose and galactose. What's the difference? Let's go carbon by carbon. Carbon number 1, is it the same or different? It's the same. How about carbon number 2? Same. Carbon number 3?
Reverse.
You got an OH on the left, OH on the left.
No, you said 3.
Carbon number 3, right there.
Carbon number 4.
Carbon number 4,
Okay.
3 down from the top, but carbon number 4, OH on the right, OH on the left. Carbon number 5 is the same. Carbon number 6, same. So what's the difference between glucose and galactose? Or, in other words, which direction the hydroxyl is pointing. Which is a chiral issue, right? Because that's a chiral carbon, that's a chiral carbon, that's a chiral carbon, that's a chiral carbon, that one is not, and that one is not. Why is that one not? Does it have 4 different substituents? 1, 2, 3. Nope! Doesn't even have 4. So, the difference between a lot of these sugars, obviously some of our sugars are going to be shorter than 6 carbon, but the significant difference between most of our sugars is quite simply flip that one, flip that one, flip that one, flip that. Which direction are the hydroxyls pointing? For glucose, all of them point right except carbon number 3. In galactose, 3 and 4 point left. In fructose, 3 is the one that points left, just like glucose. But the difference is, fructose is not an aldose, it's a ketose. Very good. It's a keto sugar. Did you miss that part? An aldose sugar versus a keto sugar?
I was like,
Okay. Aldose sugars are aldoses, keto sugars are ketoses. Yeah. So once again, we're going to place the most oxidized group at the top, show our chiral carbons at the intersection of the vertical horizontal lines, H or OH groups going left and right, and then our non-chiral groups are going to be at the bottom and or in the case of keto sugars at the top. But those are not chiral carbons. So once again, D and L, we're going to put the OH group on the chiral carbon. I should change this so that that part is also blue and italicized, perhaps even red and italicized, because it's really important. It's the chiral carbon furthest from that carbonyl. That's the one that we care about with respect to L or D sugars. Now those other carbons are also chiral. But when it comes to L or D sugars, the last one is the one that's important. And we're going to see why here in a little bit. If it's left, we call it an L sugar. If it's right, we call it a D sugar. So, here on this 5-carbon sugar ribose, we have L-ribose because the one furthest away from the carbonyl, the chiral carbon furthest away from the carbonyl, which happens to be number 4, the hydroxyl is pointing left, so it is L-ribose. Here, exactly the same thing, ribose, but that last chiral carbon, the hydroxyl is pointing right, and so it is D-ribose. L-glucose, D-glucose. This guy's pointing left on number 5, or right on number 5 over here. Where do we find D-glucose? Fruits, corn syrup, honey, pretty much anything that comes from plants is the primary source of D-glucose. It is an aldohexose, to be specific, which means it's an aldose with 6 carbons in it. The formula is C6H12O6. It is known as dextrose or blood sugar when it's in the body, which is where our previous comment about how if you go looking for glucose or glucose solution, you're not going to find it in a hospital, but it will be labeled dextrose. It is a monosaccharide, so we can use it as a building block in disaccharides or polysaccharides, so it's used in production of sucrose, lactose, maltose, and cellulose, glycogen. Glucose is the most common sugar you're going to find in normal biochemistry, from biological biochemistry, if you will. The most common sugar from organic living sources. Fructose is also relatively common. We get that in sucrose. Sucrose, or fructose itself, is a ketohexose as opposed to an aldohexose, but it has exactly the same formula, C6H12O6, which makes them structural isomers of each other, right? Because they are the exact number, that's exactly the same number of atoms, just arranged differently. That's a structural isomer. So fructose and glucose are structural isomers. L-glucose and D-glucose are enantiomers of each other. L-fructose and D-fructose would be enantiomers of each other. D-fructose is not an enantiomer of D-glucose because they do not have the same structure. Fructose is the sweetest of carbohydrates. Twice as sweet as sucrose, even though fructose is part of what makes sucrose. What is sucrose? You would call it
Table sugar.
table sugar, sugar. The sugar you buy at the store that we cook with. I have never seen, although I will have to admit I've never really looked, but I've never seen a grocery store that sold glucose. I don't think I've even ever seen one that sold dextrose. Like you could get away with, like maybe they called it, like, no, I haven't ever, so pretty much the way we get sugar, the way we commercially get sugar for our daily lives is sucrose. It's from sugars that we isolate from cane sugar.
You know Americans consume more sugar than any other country.
I did know that, yes.
It's because we're better.
And you can get fructose from both from our diet and also as a derivative of our diet, because to be fair, sucrose is a derivative of our diet. We don't get sucrose, we don't grow sucrose on trees. We grow cane sugar and then purify the sucrose from it, right? And that's what we sell. But you can also get fructose, and you guys have probably heard of it. It's something that you have perhaps been told to stay away from. High fructose corn syrup. That is a derivative of the way in which we process our foods, specifically working with corn to produce a fluid with sugar that it works as an excellent sweetener. Because fructose is twice as sweet as sucrose. So if you want to add something to a drink or a candy bar or otherwise to increase its sweetness, how sweet it tastes to us, you would want to add more fructose than sucrose. You get twice the bang for your buck if you were just adding fructose instead of sucrose. But some people will tell you that you should avoid high fructose things, that drinks that have a lot of high fructose in it is bad for you. And as much as I really don't like the sugar lobby, I am of the opinion, based on the evidence that I have seen, that you should just avoid things with crap loads of sugar, period. Because getting a lot of fructose from something with high fructose corn syrup in it is no worse than just getting a lot of fructose. It's just, to be fair, you drink some Kool-Aid with high fructose corn syrup in it, and you're going to get a lot of fructose really fast. But there's no difference biochemically from that fructose to the fructose that you get from eating an apple. You just get more of it without realizing it when you drink your high C lemonade, which is arguably bad for you. But that does not mean that anything with high fructose corn syrup in it should be avoided like it's somehow carcinogenic. If high fructose corn syrup is carcinogenic, then so is the apple that you have instead.
And yet these idiots get companies to revise their products, raise the cost.
There are a lot of things that people do out of fear and avoidance of fear, or the avoiding looking bad, even if it isn't bad. Because we could take that and then turn it to GMOs, and we could have the same discussion, but perhaps different opinions would suddenly be present about the value, quality, or danger of GMOs.
I bet you honestly using corn syrup that has a worse shelf life, more difficult to transport.
Oh yeah, but just processing just getting everything. Yeah, there's a whole bunch to it. There's some bad, don't get me wrong. I'm not saying high fructose corn syrup is good. I'm just saying don't be afraid of something that's got a lot of red in it just because they say, well, that's got a lot of red in it. Well, that's red there too. If red is bad for you, then red is bad for you. The really red stuff is just more red. There's nothing inherently bad about it because it's just more red.
Oh, red dye number 5.
Well, I'm not, this is a metaphor. Stop taking me so literally. Honey is sweet in the way it is because honey has a lot of monosaccharides in it already. Honey is also one of my favorite naturally processed foods because it's taking, honey is something where we get bees, and bees make honey, and we act like it's this beautiful and pure thing, and don't get me wrong, I love it. I love honey, but we're literally treating bee throw up like it's gold.
It is.
It is, yeah, it's gold.
Yeah, the color.
I mean, have you ever looked at how much it costs to buy this stuff? Like, I buy 15 pounds of it at a time. But see, it's even worse for me, because I take bee throw up, and then I intentionally add a bunch of fungus to it to get a pustulistic infection, and then I purify the waste from that, and that is what I serve in a glass cup to my wife when it's for special occasions where we both celebrate booze.
Tuesday, Thursday.
Yeah, or yeah, like a special day, like any day that ends in Y. But
It's not always gold. I had somebody bring back some honey from Georgia near the Crimea.
okay, yeah.
And it was completely pale.
Mm-hmm.
The lightest, I don't know what flowers, but the lightest, so much lighter than even clover honey. So I grew up in Los Angeles where it's all orange blossom honey,
Right.
which is just almost cloying. And then get back here and it's this wonderful light clover honey, and then this stuff from Europe. Oh my goodness.
It's the same. It is different in the same reason why rye is different than rum. It's all of the other stuff that comes with it, right? But the point is that, and the reason why I bring it up is that honey is this beautiful thing because bees are taking products of plants and they're pre-digesting it for us, and then throwing it up into their storage containers that they keep in their hive for later use, and then we harvest that, jar it, and sell it for like way too much per pound. But it's really tasty.
At least it's not poo.
There are a lot of things that if you really understood what it was you were eating, you might not be so terribly interested in eating it.
No.
But as long as you don't know, you're just like, oh, this is delicious.
You just can't give children honey.
Well, up to a certain age, you're not supposed to. I don't know how much of that is.
I know. They always tell you that though.
Yeah, the same thing about don't give them eggs until it's, I'm like, really? I don't see when we were on the plains of whatever country it was, that mothers were going, no, put that egg down.
Yeah.
Like if you found an egg, you're like, eat the egg, kid, there's a lot of protein in that. Well, you probably didn't say that either, but eat the egg, kid, that's good for you. Don't know when your dinner's coming next. That type of thing. I don't know. But yeah, nowadays we can be much more intelligent, or not so much. D-glucose, D-fructose. That's what's in honey that makes it so incredibly sweet. Galactose is another example. This is another aldohexose. Notice the formula. C6H12O6. Saw it before. We get that from the disaccharide lactose. You guys have heard of that? Lactose, right? What's the problem with lactose? Lactose intolerance is a thing. It is a thing that is actually one of the best examples of modern day human evolution, following the movement of the gene that makes us lactose tolerant. Because here's the reality of the situation: all of us are lactose intolerant. It's just the degree to which we are and when it occurs. That's what matters. And so, following that particular gene as it moved through populations. It's an interesting study.
Don't they say the reason you're lactose intolerant is because our bodies aren't made to digest lactose past a certain age?
Thank you for saying past a certain age. Yes, exactly. And that's what I mean by the gene. Here's the thing. Okay, we'll come back to this in a moment. Because there's some slides specifically about lactose that are going to be topical, and so it'll remind me, and we'll come back to this. So we'll just shelve that conversation for a second. So galactose is similar to glucose, except for the OH on carbon 4, which is flipped in the opposite direction as well. We have this condition called galactosemia. It's an enzyme that we need to convert galactose to glucose. So if you have galactosemia, then you are missing that, which means that it is difficult for you to do anything with galactose.
Where do you find galactose in foodstuffs or whatever?
It's a product of lactose digestion, so milk. Milk breakdown. So, hyperglycemia and hypoglycemia. Normally in your blood you want to have a glucose level of 70 to 90 milligrams per deciliter, which is actually fairly low level. We have glucose tests to measure your glucose tolerance. So we have you drink something with a massive amount of sugar in it.
Nasty.
It's one of those things where if there's anything that proves you can't have too much of a good thing, it's that. Because when it was like, well, I love sugary sweet food, so obviously just more sugar must make it better, right? No.
It's like syrup.
Yeah. So, here's the thing though. We give someone this test and then measure after a certain period of time. If they have normal, if they're normal blood sugar levels, if their blood sugar levels stay relatively normal after that 4-hour period, then you're good to go. If you have too much hyperglycemia or too little hypoglycemia, then that means that your body is not capable of normally regulating blood glucose levels, which means that you need to be managing your blood glucose levels yourself.
What I don't understand is all the flavors for that are disgusting, and now that's what. And now, when you take the Go Lightly and you're going to have an, colposcopy, it tastes. They have the same flavors now. They flavor it with these same things. And I'm like, they were nasty for that test. Why are you going to do it for both? Makes no sense.
Oh, thank you.
I imagine it's one of those things when when you have a captive audience. Like when I was a kid, all medicines just tasted nasty. But now half of them don't, and I know this because there are some medicines I can give my son. If he sees my daughter get her antihistamine, he has to have some too. Like he begs for it. But then there are still other things, certain cough medicines that we've got where she's like, oh, that tastes bad, Dad. I'm like, you child, you have no idea. Like bad for her is, ew. Like no. When I was a kid, bad was like plug your nose and just like throw it back like you were already an alcoholic or something, and then just not breathe for 30 seconds, like ugh. Anyway.
And then everything became bubblegum.
Yeah, exactly. But even that was nasty, and now we've got this nasty bubble gum. But now we've got all these other flavors, and I don't know, some of them work. Anyway, so diabetes mellitus can cause hyperglycemia. So hyper means more, right? So hyperglycemia, so you have too much. It occurs when the pancreas is unable to produce significant or sufficient quantities of insulin. So, when in the absence of that insulin, then glucose levels in your body fluids can rise as high as 350 milligrams per deciliter. And that can cause thirst, excessive urination, because your kidneys are working overtime to try and get rid of that sugar, increased appetite, and potentially weight loss. It also has a bunch of other problems, including you can lose your toes, you can go blind from glaucoma. There's all sorts of problems with way too much sugar, because your body is a very fine-tuned, exceptionally complex machine, and you throw something as important as your sugar levels completely out of whack, it's gonna up, like pretty easily. Insulin, what's that doing? The slide isn't telling us. What's insulin do? In the absence of sufficient insulin, your blood glucose levels rise and or stay high. So what is insulin doing? It regulates your blood sugar, but specifically it regulates it in one very specific direction. Down. Where does it go?
Gets packaged by your liver and glycogen.
And everywhere else as well. Yes, it goes into your liver. Insulin tells your liver to take up sugar and turn it into glycogen. It tells your muscles to take up sugar and turn it into glycogen. It tells everything to take up sugar, but mostly your muscles and your liver.
I thought the muscles got glycogen from the bloodstream from the liver.
They have a small store themselves.
Right,
And then when it empties out, when they run out, the liver doesn't release glycogen into the bloodstream, it breaks it back down into glucose and releases that. So the liver is like the big bank, central in New York or whatever, and then the muscles are kind of like the branch location. They have a little bit of cash, but when they run out, they got to get a big truck for
I
it.
knew the muscles stored it, but I never heard that they packaged it.
It is my understanding that they can synthesize it, but not very much. I might be wrong. But yes, the workhorse of this is, you have Google. The workhorse of this, yes, is the liver. But all cells will take up sugar in response to insulin. Insulin lowers the blood glucose level, or the glucose level in your blood. Because if that stays too high, bad things happen.
Diabetic coma.
Up to and including death.
Either way, that people act the same whether it's too low or too high. Confused, falling over.
Right.
The machines in the hospital top out at 500. I always like it when you test a person talking to them, and the machine says, not capable of.
Yeah, beyond
Yeah,
limits. Like,
you're like, what?
you should not be talking to me.
Yeah. It's because they get used to it. Your body starts to get used to it.
Here's the thing.
You're correct, sir.
Thank you. Here's the thing about blood sugar levels or otherwise. Why this is so important. Does anybody know somebody who actually is hypoglycemic?
Mm-hmm.
So so if they're bad enough, what do they carry around with them?
Sure.
Sugar,
Yeah.
or specifically,
Insulin.
no, insulin is diabetes.
Some form of complex carbohydrate
Yeah,
starch.
peanut butter.
Peanut butter. I had a
Milk.
friend who had hypoglycemia that was bad enough. He carried around fructose tabs.
Yeah.
Because here's the thing. Hypoglycemia is a problem where your blood sugar is too low. And your blood sugar is low, that's not really that much of a problem other than the fact that if your blood sugar is that low, your cells there's nothing there for your cells to absorb. And so when your cells start to run out of energy, if they run out, right? And so what happens if you start getting hypoglycemic is your body starts shutting down because it's not getting the energy that it needs to actually do what it normally has to do. And so frequently if you have really bad hypoglycemia, minor, yes, carry a Snickers, sugar cubes or something like that, that's fine. If you have really bad hypoglycemia, you'll carry around fructose tabs. Because fructose can get directly into your cells.
Yeah, you put
It
in
can
your
pass
cell.
through the cell membrane. So it can supply your body with energy like that. And you will absorb it right on the tongue. It will dissolve in your mouth, immediately into your bloodstream, and it will increase your blood sugar levels. Your cells will get energy from that. And then you, of course, also need to eat something so that you can get a normal sugar dose from that.
The other thing they carry around, it looks like, you know those little bitty icing tubes?
Mm-hmm.
They carry those around. And on the ambulance, we stick that on like a tongue depressor.
Right, yeah, right. And the reason that under normal conditions, glucose or fructose, sucrose, just a nice sugar thing, that would be enough. But the problem is that when you have diabetes, if you do not have an appropriate insulin response, your cells don't take up glucose fast enough to replace it. If you have a problem, you have to tell your cells, open the door and let glucose in, because glucose actually has a very low permeability for our cell membranes. We have to assist the transport of glucose with a receptor that pushes it through the membrane. Fructose can just get in on its own, but glucose needs a little bit of help. Insulin tells the cells to open that door and pull in a lot of sugar. And so if you are diabetic and you have a lot of sugar in your system, without insulin, you have similar problems. That's why hypo and hyper have similar acute symptoms, because the problem that those symptoms are coming from is, for the most part, because cells are not able to get the energy that they need, because they're not able to get the sugar that they need, because they do not have an appropriate response to insulin. Either because they're not making enough of it, or because their cells aren't responding to it.
The response I always have that I find paradoxical of the hypoglycemic event is muscle shaking. Doesn't that take a huge amount of glucose to to make that happen?
No, what it takes is a dysregulation of calcium entry into your muscles. And so the lack of being able to coordinate that could cause some shaking. Yes, if you completely ran out of energy, it wouldn't shake. Yes. If you had no energy at all, because the calcium entry into your muscles that cause the myosin alteration that actually cause them to contract, that is ATP dependent. So if you completely ran out, that would not work. But under low sugar levels, you also have a hard time regulating the calcium pumps, and so the calcium levels in your muscle cells can fluctuate enough that you can get what would feel like tiny little spasms everywhere, all over the place, as opposed to cramps, which are a different thing, but also related to calcium.
People can actually contract when it's messed up too. Their muscles will start contracting, and they'll turn in.
Yeah,
The other thing you can
fasciculation syndrome, so I get the cramps and the fasciculation.
You can smell it on their breath a lot of times too. It'll smell like
their
they
breath
drank
will
a
smell
whole
sweet.
bunch of schnapps or something.
Yep, and that's because of the amount of sugar that's in their bloodstream, that's in that liquid, and so it increases the gas pressure.
Same
so
thing with the
they
urine.
literally have sweet breath. It's one of the diagnostic aspects of somebody with diabetes that's undiagnosed, is that they have sweet breath.
And the urine too, it'll be.
High in the urine. Because the kidneys will still try and get rid of the sugar regardless of whether they have an insulin response. But that's one of the reasons why diabetes can also lead to kidney failure, because you overwork the kidneys and they shut down.
You can tell a lot by urine.
Yep. Let's see. Hypoglycemia, when the levels drop below 40, overproduction of insulin, or just because you're not maintaining your blood sugars low enough otherwise. So once again, insulin, the response from insulin is to tell your cells to take up more sugar, which is why when you eat, your body responds by releasing insulin to tell your cells, by the way, we've just had a meal, everybody take in some sugar now. Which is why if you're diabetic and you're about to eat, or you have just eaten, you're supposed to calculate about how much you ate and dose yourself with enough insulin so that you can mimic that response. But you do too much, and you're going to get shaky. You do too little, you're going to get shaky.
And low is worse than high because your body shuts down quicker and
Right.
you go into a coma way faster.
And so you can't solve it yourself if you're not thinking clearly enough to do something about it.
You will do crazy things.
All right. Let's move on past that and talk about Hayward structures. But let's do that after stretching our legs for a bit, because it is 7 o'clock. 7:03 by my watch, so let's take a 10-minute break. I'll go get myself some more water. And we'll try and get through this. I do want to, by the time we're done, if we don't finish this today, that's fine, because we do have a little bit of spare time in the syllabus this week. So I wanted to know if we wanted to go over some chapters on Thursday or move on, and therefore have a little bit of spare time at the end of class instead. So but we'll talk about that at the end of class tonight.
Our test is this week too, right?
It is. Oh, it's Friday morning.
Wait, our test is this week.
Our test is this week.
Are we?
It goes fast. Exactly. After this, we are done.
So you see this?
Since I'm in school, I've been like homeschooling my son with different stuff. And
That's quite advanced stuff. I mean, this is basically teaching me what to go look up. I meant to go there.
Yeah, there's two different nursing classes, and the only difference is the Tuesday, Thursday.
Yeah.
Tuesday, Thursday class is at 9 a.m. and the B is in the afternoon.
So have you seen the Minecraft body? It's for kids. I wish there was a
I know you're going to be so excited
more
for test.
adult.
No, because
So,
when I was
like,
going out of town
I
next week, I
was
was
trying to
trying to
show
figure out how I was
somebody-
going to take
I
that.
haven't seen that one.
I was going to ask, like, can you just post the test like a week early?
Trying to show somebody.
No test. It's this
I
week.
said you probably recite
Test
more than I
number
can.
3.
Yep.
So,
Which is
I got
definitely taking a lot more work on
injections
my
into
part to
sets.
build it.
Oh, I'm
because
sure,
there was the
because of all the.
so turn on the-
Chemical structures and everything.
Yeah.
Like I found a freeware software
Is that what it's
that allows
called?
that I
Is
can
it a
use to draw
downloadable
chemical structures.
My incredible
Play
body.
Store?
But then I've still got to save that
Yeah.
as an image and then
But
import that image
it's not
into a
cheap.
question and give it the alternate hyperlink for the text if the image doesn't load. Like,
The base one might be freebie if you have
That
modules.
sounds painful.
But I was able to
Kind of.
show where I was getting the injection
You could just,
by, going.
Give it to us.
oh sure, yeah. Just like
You
everybody's,
know,
you're all
you
good
can
on
turn
this,
all the
right?
different
Yeah.
I'll just take your word for it.
Systems,
yeah.
and it's actually narrating, so if I want to put the margin test in there, it'll tell me that. Pretty cool app.
That's not bad.
Yeah, but how much comes with it is the question. I bought it for,
Body parts adventure for a kid.
when I babysit my nephews, I always wanted to play puzzles.
All my son wants to do is do stuff with math.
Poor darling.
I'm not a math person, so I can't help him there.
Right. But you can help him spend the Nobel Prize money when he
That's true.
eventually.
He said he's gonna take care of Mom when she lives on the second floor. I think it's just because he's the baby.
A lot of times that's the one that doesn't take care of him.
I think it's also because he's a boy. What was the other one?
The My Incredible Body and then SW Physiology.
I bought some really cool,
Oh, this might be the, oh wait. What happened? I don't know, but apparently I have to buy every single.
one. I got some really cool flashcards for physiology. I take physiology next.
Yeah. You,
Oh, that's right, we have it together.
I wanted to find out about
And then I have anatomy,
that. Mm-hmm.
the second.
Which
Late
one?
fall. You already taken anatomy?
No, we have the same
We have the whole
classes.
same thing.
Now, we might be in different sections. No, I'm actually glad to have someone I know and like in the cohort, in the same cohort. I think that's,
I'm like that too, because if I'm gone, I can be like, hey, I was
Right.
gone, hey, what's up? I have that, well, I know another girl, then she's in my, microbiology class right now, she'll be in class with me, and she's really good, she's just now. But she's really smart, we have lab together, well, both of them.
so,
Because we're having too much fun with our experiments in lab. We're kind of goofy.
you're just doing what, at this point, you're doing colonies and inoculate. You've already done inoculation.
Right now, we just took samples from home, that was our thing, is what we wanted to do.
Fomites.
Yeah, now we're focusing in on what exactly it is, and it's grossing us out. It grossed me out so bad that I went home and had OCD, and like cleaned out my fridge, and like redid everything to where it was in glass, and like,
10 canisters of Clorox wipes. See,
yeah, I went to Sam's, bought those Clorox wipes, and then I bought all these containers that are glass, so I'm not in plastic anymore, and did all this crazy OCD stuff.
I intentionally keep my life a couple steps above squalor because I want my immune system.
Yeah.
Or fomite.
I have kids, so my immune system, they bring home so much crap.
It's physiology.
I know, it's kind of funny, not working in top school, I've been sicker now, and I don't know what
I'm in OCB.
And that's this week, and then
You're no
2
CA?
weeks after that, which is the 8th week,
to do. Yeah,
Crap.
and then,
Oh well.
because I know the 7th week I have
I didn't
it,
wanna go
um,
till 6 o'clock,
I have
Yeah, but that means you have to go
a
later
paper due.
on those other days,
It's
don't
6
you?
pages, not that bad.
No, Monday, Wednesday are the same time.
Right.
It's the Tuesday, Thursday.
But
I didn't wanna be in
10
class all the way till 6 o'clock at night.
What's another 2 pages?
I'd rather be in class
Is it like
9 to
research
2.
or not? Or whatever.
Yeah, that's a whole research one.
Oh, that's not bad.
That's easier than the first paper.
I didn't know the reason, I thought, I think.
See, I had a Spanish class at 2 o'clock.
That's not, it's
So-
not bad.
That's not bad for.
I went 9 to 2, so I go straight from there.
Yeah, I had a 10 page paper once, that
Oh,
was
Tuesday.
terrible. And then some people, my cousin had to write a 20 page paper before.
Yeah.
My
I think it's
master's
partially
thesis
this is just,
was
so
97,
Oh,
and
I
my
have to wait
PhD dissertation was
to
130.
to work.
that's terrifying.
Is that why most professors just write books after?
I don't know, maybe.
I mean,
I mean, it's not exactly the same, but it's just like, you go through that
It just
experience
worked out
and,
for me,
and
'cause
then
how I,
you look back and you're like, oh, I've got this
history
5 page paper I
class I
have to
need
write,
to
and
do,
now I'm
and
like,
and I have to have 2 more.
5 pages,
'Cause I'm getting
5 pages is
my
nothing, I
bachelor's.
can just,
Right, you can knock
BS
that out.
I'm gonna get my
5
associates
pages,
first,
like
then I'll
this.
get my bachelor's.
Yeah.
I already
Yeah,
have
unless
almost,
somebody else.
See, I,
produces
like,
lectures.
When I was in high school, I never really wrote papers.
but I've already got all my credits except
And
for the
then,
actual
you know,
nursing
my
bachelor.
first year of
The
college,
only
I had
things
to write
I
this
don't have
10
for
page
bachelor's
essay, and I'm
degree
like,
is my
I could see that with you guys.
And one from
Because
Right,
it's
yeah.
like iPads galore.
Well, and I, you know, I've had friends recent, and I remember that too, I remember being
I might not have the
intimidated by a
ethics one,
10 page paper.
but,
And then, you know, and I have friends that have gone through college recently that also were freaking out about a 10 page paper. And
You have to-
I
you
get
have to
it,
get
you know, like,
that
a good 10 page
Yeah.
paper, it's not
Because
like, oh, that'll take me 5 minutes.
Everybody,
but
even
still,
the,
Right.
because, you know, but it's another one's aspect of memory otherwise. I think about
you don't wanna take,
the way I wrote my master's
you
thesis
don't wanna take.
was by going to the library
Ethics review.
Was it
first thing in the morning.
It's horrible.
daily?
Horrible.
Yeah,
You said
and
you
then
did.
leaving the library to get lunch, going back to the library, writing. So it's like, there was 2 weeks of
But
that.
I did okay, once you know his.
And that was the first draft. And then beyond that, it was editing. But yeah, first draft was 2 weeks of almost 8 hours a day at the
I
library.
had him at 9
So,
AM last semester.
Yeah,
And I was just like, I'm not a morning person
you know,
anyway.
so just
And I'm
comparatively,
just
10 pages is still a big deal. And 90
But I still
pages was
gotta
also a
be-
big deal, but it took me 2 weeks of like, that was my full-time job. So, but it just, afterwards, you don't really remember how much of it is, you're just like,
He's way smart.
I wrote a 90
He
page
makes
thing, 10
everybody supposed to be
pages is
smart.
nothing. Still a thing, but yeah, it's certainly not as
Sounds like
daunting.
that would be something,
Well, it's just like 10
you know,
pages.
university
when,
has a
you know, you're
reputation
stuck
for
in an
course
English
being bad.
class where all
I think they
you're
want to
learning
trust.
about is like just
It's-
basically
it's
Shakespeare.
warning.
Right, 10 pages about something you don't care that much about.
That
Yeah.
teacher
Right,
so
that's
well
the problem, is when you're really hedged in by the assignment,
Because then I read them.
that's the part, like, how do I write 10 pages about the
the
specific thing I was asked to write about? Because
I
my,
like it.
your dissertation, your thesis, you're writing about,
Something you like.
right, the thing you've been working on for a year or 3, like, the thing you're really knowledgeable about, so it flows a lot easier, it's, you know, so then it's a matter of limiting yourself for how saying things cogently, right? But yeah, trying to find a way to fill up 10 pages within a very narrow limit, that can be very daunting.
See, I'm already registered for that.
You end up making up words. I'm like, I can't.
Well,
Yeah,
if it's a Shakespeare paper, then that's just,
Well-
I'm the only
Up
one
above.
registered in that mine, no CA.
alright, let's get back into chemistry, shall we?
Hey, you need food. You don't put it on the script.
Alright. Just try.
I'm working on that.
Alright, so, when we talk about sugars, very frequently what you're going to do is you're going to see a sugar drawn in a Haworth structure. And that's the ring structure of sugars. That's because, especially in aqueous solutions, this ring structure is the most stable form of the sugar. And so it's going to spend most of its time in this ring structure instead of as a linear sugar. That being said, you should know, and we will specifically talk about the interchangeability of this, once it forms this ring structure, that is not permanent. It can become linear and then recircularize, become linear, recircularize. It's going to spend most of its time as this circular sugar until it is locked into that shape via other chemical structures. But monosaccharides can quite easily shift back and forth between their linear and circular structure. It's just that the circular one is more stable, especially in an aqueous solution. So how do we do this? How do you turn this linear sugar that we've been talking about so far with our aldyl or ketone carbonyl group near the top, with all of our chiral carbons down here in the middle, and then our non-chiral carbon at the bottom? How do we turn that into a circular ring structure? And so the first step of that, conceptually, is just taking this entire thing and turning it on its side. So 90-degree rotating onto its side. It's still exactly the same thing. All we've done is change the orientation of the OHs a little bit, but all of the hydrogens and hydroxyls on the purple box on the left are now on the top. All the hydroxyls in the green box on the right are now on the bottom. One could argue that the oxygen is pointing the wrong way, but that's okay because that's the way that we're going to bend it here in a minute. So that's why that carbonyl group is pointing in that direction. So once we have turned that on its side, this is, by the way, an example of D-glucose. Once we have done that, it takes a few other steps for us to be able to appreciate what's going on here. So now what we're going to do is we're going to take this linear chain and we're going to bend it back on itself so it points back towards that carbonyl oxygen. So that's what's happening here. 1, 2, 3, 4, 5, 6. All right? So we have bent that back around so that that 6th carbon is within reach of the 1st carbon. Everybody see how that works? Now, if this was a 5-carbon chain, we would do so the same. We would bend it back around so that that last carbon was within reach of, more importantly, that double-bonded oxygen, in fact, because that's the thing that we're reacting with. So we need to get that last carbon relatively close to that double-bonded oxygen. But we do not actually react with that last carbon, because that last carbon has a hydroxyl pointed in the wrong direction. So what these arrows are showing you, and how we're moving to this 2nd group right here, is we are doing what I did previously to that one single carbon, right? This is a single bond, so that means this carbon can rotate. So what we're doing here, these arrows do not mean that we are making some sort of a chemical substitution. It means we are literally just reaching into that carbon, putting our fingers on the sides of those 3 bonds, and just turning it 120, or more specifically 109 degrees, as it were. We are rotating that bond around so that the hydroxyl is now pointed more at that carbon and that double-bonded oxygen. So that means that carbon number 6 that was pointed at the oxygen is now going to be pointed up where the hydrogen was. The hydrogen is now going to be pointed down where the hydroxyl was, and the hydroxyl is now going to be pointed towards that double-bonded oxygen. So what's going to happen here in water, in an aqueous solution, is that oxygen is going to make an attack on that carbon. And what we have here, if you'll forgive me, kind of drawing it like this, is kind of like this, where we have some stuff here and some stuff here, and the potential for attack there. So what's going to happen is that oxygen is going to form this bond right here with that carbon. That hydrogen is staying where it's at, and that hydrogen is going to bond with that oxygen there to form a new hydroxyl. So this bond right here, we'll call it number 1. This bond right here, we'll call it number 2. And so this here is number 1, and this is a really weird looking E on its side, number 2. Everybody follow? Yes?
I got so confused between step 1 and step 2.
Step 1 and 2? So this one and this one?
No. Previous slide.
Yep.
Because I'm just trying to figure out, okay, I know you turned it 90 degrees, but then why is it now OHCH2, or is that?
That's just this, written in reverse.
Okay, so we're working.
O, C,
Right.
H2.
So when it gets to like step 2 on here, then it shows up like CH, is that, so we're moving the hydrogen around?
Yeah, so
Okay,
so first off, let me just put another box here so that you can see this clearly.
okay,
This box here
right,
is this box here.
that's fine.